So this room is packed. Hopefully you're all comfortable. So today I'm talking about modern chess engines. Just as a quick check of the audience, how many have heard of chess engines? So almost everyone, that's good. Minimax and alpha beta pruning, a decent number. Evaluation functions, okay. Null move pruning, toward, and then Bitboards, also toward, and some others. Okay, cool. So let's get started. So a quick overview of what I'll do over the next hour. What are chess engines for the 1% who don't know what they are yet? How they work is most of this talk. Testing chess engines, and then maybe some time for questions at the end. And Tord will also help answer questions at the end. Okay, so first question is, what are chess engines? Basically, they take a board, state representation, and output the best move is the simplest way to think about it. And this is like a giant simplification, but that's what they do. Everyone, I think, knows about Deep Blue. So in 1997, it defeated Garry Kasparov, who was the reigning world champion at the time, 3.5 points to 2.5 points. It ran on IBM's giant supercomputer at the time, very specialized hardware. It had chess chips, so like special chips that made some operations faster. And it had a typical search depth in the middle game of 6 to 8, and sometimes it reached depth 20. So depth is in half moves. So white and black moving is 1 move or 2 depth. And then now, it's 2015, it's been 20 years, we have Stockfish, which is much stronger than any human grandmaster. It runs on any personal computer. And so the much stronger than any human grandmaster part is, say, on a standard quad-core machine. And it reaches depths of 40 plus in standard time controls on like relatively decent hardware. So like 8 cores maybe. Core authors, Tord Romstad, who is here right now in the first row, Marco Kostalba, and Juna Kiski. It's one of the best engines. I say one of because Komodo technically right now is topping Stockfish just a little bit in some rating lists. It's cross-platform, so it runs on Windows, Mac, Linux, iPhone, Android. It's free. It's open source, so you can find all the source code on GitHub. You can contribute as well. And here's the pitch. You should all go to stockfish.io to download it. This redirects to stockfishchess.org. This is just easier to remember. And yeah, it's all the platforms, so you should try it out. I guess everyone's familiar with chess engines, but there's that Carlsen-Anand game where Carlsen made a blunder, and then Anand missed his blunder, which is fun to analyze. So let's try that out. So let's see. Here's Stockfish. Move this window over this way. OK. That kind of fits. So yeah, so this is move 25. Let's see. Yep. So Anand had just played this move, rook dg8. And the score is currently plus 0.66, so that's about half a centipon in favor of Carlsen. And so he was supposed to make something like rook g3 as his move, but then he did king d2. And so the score jumped down to negative 1.15, which means black is now winning by 1 pawn. So black was supposed to take the pawn, but Anand missed it for some reason, and instead the score jumped back to plus 0.9, so Magnus had a lucky moment there. So that's a demo of how it works. So centipawns are the main unit of measure, plus is white's winning. So right now it's at depth 29, it's just running on my laptop. So yeah, now back to the talk. Mouse is this way. Okay. Okay. Yeah, so that's how it works. You should all download the chess engine if you haven't already. Okay, so how do chess engines work? Well, Since everyone's familiar with Minimax, here's this cartoon illustration that I spent a long time on making. It's essentially, you're this happy face over here. You think about all the moves you could do and how your opponent might respond to those moves. He thinks about all the moves you can do. It repeats ad infinitum until the end of the game, at which point it bubbles back and you have your score at the root node and the corresponding moves that will take you to whatever leaf node that you want to get to. So here's a search tree. We can all label it. So here, red is trying to minimize his 3 moves. He chooses -5. Over there, he chooses 0. And over here, he chooses 2. And then green is maximizing over all these nodes. So he picks 2. And that is the move that leads to the best result. Here's some pseudocode for Minimax. So if you're the maximizing player, you call yourself again, except now you're minimizing, you take the best value, and you return that. If you're the minimizing player, it's basically the same thing, except you try to maximize. There's a lot of duplicate code on this slide. One might think, wouldn't it be great if we could eliminate these if-else blocks and just get one for loop? And you can. So remember that chess is a zero-sum game. That means that, well, if someone's winning, someone else is losing. So we can exploit the zero-sum property of chess and also note that the maximum of A and B is the negative of the minimum of -A and -B to rewrite the code in this way. So this is called negamax. And essentially, where we used to call minimax with now you're maximizing is not the maximizing player, we simply negate the negamax value. We always maximize, and this accomplishes the same thing without the duplicate code. So it's just a nicer way of looking at it. Stockfish is written in a negamax framework. So you should just get used to this way of writing minimax. Efficiency of minimax is pretty bad. Well, when you apply it to chess, because it's branching factor to depth. And the branching factor in chess in the middle game is about 35. You have 35 moves that you could do, and an average chess game is 50 human moves, which is 100 alternating, and that's a very big number. If each position takes 1 clock cycle, which it doesn't, it takes more than that. But if it did, then it would still take many, many, many universes to go to the end of the game tree. So clearly, we need a solution for this. And one way we do this is we limit the depth of the search, right? So here's our entire search tree. Here's the end of the game. And so we just draw an artificial line and say here, instead of calling minimax or negamax, we just return a static evaluation of the board. So some sort of number that represents how good the board is. And obviously, the farther down you scoot that line, the better it is. And so you might ask, well, what if you have an unknown amount of time? You can't just say, I'll only search to depth 10 and stop. Well, the solution is called iterative deepening. So you start at depth 1. While you still have time left, you do a search at depth 1. And then when that finishes, then you say, OK, now I'll do a depth 2 search, a depth 3 search, and so on. And now you might say, well, doesn't this waste a lot of effort, right? It researches something again and again and again, and you've already done, like, say, a depth 5 search, and now you're going to depth 6. And so the answer to that is 2 things. One is the bottom layer is always the most time-consuming. So once you go to your +1 depth, the amount of time you spent before is inconsequential. And second is you learn stuff from previous searches. So you might, as we'll learn later in alpha-beta pruning, move ordering really affects the speed of the search. So when you're on your previous iteration, you can change the move ordering that you'll use for your next iteration, so your next iteration will go faster. So that's iterative deepening. So what are some sample evaluation functions? So the ones that most humans use is, well, an evaluation function is a linear combination of features with weights. And so most humans use something like this, right? So they evaluate the number of white queens minus number of black queens, and same for rooks, knights, bishop, and pawns. And their weights that they assign are 9, 5, 3, 3, and 1. So this is a simple evaluation function. I should note that in Negamax, the evaluation is always relative to the current player. So this is, in the Minimax framework, you would do absolute. But in Negamax, since you keep flipping the sign, it's relative to the current player. Obviously, chess engines don't just use that. There are a lot of other techniques you could add to make the evaluation smarter. So I'll just go through some of these. So tapered evaluation. When you're evaluating, you might use a different evaluation function for the middle of the game versus the end game. For example, you want your king to be closer to the center in the end of the game, but you might want it to be, or you do want it to be closer to the edge, the bottom right or top left, or in one of the corners in the mid game. So you'll calculate two evaluation scores, and you'll basically combine them. And it's called tapered evaluation because you taper off the evaluation of the middle game evaluation as it gets closer to the end game. And you might use a number of pieces as a rough heuristic for which stage of the game you're in. You might give a small bonus for having a bishop pair, because having a bishop pair means you're covering all the colors on the board, so that's good. Piece square tables are a way to drive certain pieces to occupy certain squares. You might want your pawns in the center of the game at the beginning, so you might give a small bonus, like +1 or whatever metric you want to use for having pawns in the center, or knights not at the edges. You might give a huge negative score for that. King safety is something that you want to evaluate, so maybe how many pawns surround your king, whether there's a rook next to your king or not. That will encourage your king to be protected. There's mobility. So generally, you prefer positions where you have more options available to you. So you might use the number of legal moves in that position as a score for mobility. You might also potentially do single piece mobility, so you don't want your queen to be trapped. So you could add the number of legal moves your queen can do to your evaluation function. Pawn structure, so a small bonus for having pawns in a chain, because we know that isolated pawns or double pawns are much weaker. They can't support each other or advance to the end as quickly. And then maybe a small bonus for rook on an open file or rook on the 7th rank, and so on. So all of these are things you can add to your evaluation function to make it smarter. This is in case any of you want to write chess engines. So now let's discuss the horizon effect, which is something that you get as a result of limiting the depth of the search. So here's a scenario. You're an engine. You're about to lose your queen, but you're only searching to depth 5, right? So you could, all your moves are bad, except you could sacrifice your rook, subpar move that you do right now that is really detrimental or doesn't forestall a detrimental move. So the solution here is quiescence search. I hope I'm pronouncing that correctly. So where you would normally just return the static evaluation of a position, you search positions that are interesting until to greater depth until the position becomes quiet, so to speak. And one definition of quiet you could use is that no captures are possible, right? So you exchange all pieces at your leaf nodes until there are no captures, and then now the position is relatively quiet, so you can use that static evaluation more confidently. So that's quiescent search. So alpha beta pruning. I think we're all familiar with this, but Tord actually had a great example of how humans do alpha beta pruning. So say you're the green node up there, and there's this giant tree over here, and you evaluate that it leads to a draw. And then, so that's your first move choice. For your second move choice, let's evaluate this. So there's a minimizer node over there, and the minimizer has these 5 options, -9, 4, 7, 3, and -2. So once you evaluate this node, then the score at the minimizer node is now -9. But you know that -9, losing your queen, is far worse than just this score that you already have, which is a draw. So you don't need to evaluate any of the remaining nodes because you know that the minimizer node value will just keep decreasing, and you have something that's better. So you would never choose that node. So formally, if you're computing the minimum value for a node, the value keeps dropping. Let alpha be the best value for the maximum node. If ever v becomes less than alpha, you would avoid it. So you can stop looping over the children. And there's very similar logic, actually mirror logic for the variable beta for computing the maximum value of a node. So here's the pseudocode for that. In the negamax framework, you just add alpha and beta as parameters, and you have your breakout condition. It's now when you exceed beta because we're at the max. We're always maximizing with negamax. So there are some properties. It's backward pruning. It does not influence the root value of the node. So if you run minimax and you run alpha beta search, you should get the same result. The values for non-root nodes are either an upper or a lower bound because they could have been pruned. If you have better move ordering, you will get more pruning because your bounds will be tighter when you go down the leftmost branch. So you will be able to cut off more nodes to the right in your tree. And the time complexity is O of b to the m over 2 if you have perfect move ordering. So you've essentially square rooted the amount of time it takes to run search, which is pretty good. Now let's talk about other. So this is kind of like a survey of topics. That was search. We'll talk more about search, but now here is a way to speed up search in a different way. So in chess engines, you often run repeated searches. So you'll make, say, a search on the root position, on the start position, and you want to do E4. And then your opponent might respond with E5, which is what you anticipated. And now you're rerunning that search again. But that search is a subtree of what you had originally searched in the first place. So wouldn't it be great if you could cache these searches? And you can. So you hash the position that you're currently at in your search. And you store the move, the flag, the depth, and the score. So the move is the best move, or not necessarily the best move, but a move for that position. The flag is whether the search was exact, an upper bound or a lower bound. The depth is how deep that subtree got, and the score is the score for that position. So every time you run a search on a position in the negamax code, you would first check your table to see if you have that position. If you do, great. If the depth is better than what you have, if the flag matches what you need, then you would just use that result. If the depth is less than what you need, then you would continue rerunning the search. After you run your search, you would store that back in the table. And you might ask, well, isn't hashing expensive, right? You wouldn't want to compute the hash because the search is run many times per second. And so you don't want to have expensive hash functions to uniquely identify your board position. So the answer here is Zobrist hashing. It's a way to incrementally update your hash as you go. So when the engine is initialized, you generate a bunch of random numbers. These map from, say, white's pawn on A4 is mapped to a number. White's pawn on B7 is mapped to a number, and so on for all colors, pieces, and positions, so squares. So you have 64 times 12 times 2. And so say you're currently having this hash, and then white does knight B1 to C3, and it captures a bishop. So you can simply XOR all the corresponding moves that you've already generated, right? So you have a number for white's knight on B1, so you XOR that, which essentially removes that knight from B1. Then you XOR in the black bishop, or you XOR out the black bishop on C3 because it got captured, which removes it from the board. You then XOR the white knight on C3 to add the knight into the board, and then you XOR your change sides number, which flips it so that a hash for white does not collide with a hash for black to move. So that's how Zobrist hashing works. Oh, and then I just picked some other random number just for effect. So there it is. So now we can discuss forward pruning techniques. Just to check, is everyone following? Am I going too fast, too slow? No response. Great. OK. So forward pruning techniques, I'll only cover 3. I think if you attend Tord's talk after lunch, he'll cover these probably more in depth. And these are techniques that do change the result at the root node. So using these techniques, you might miss something. But most of the time, they're pretty good, and they considerably shorten the amount of time it takes to reach a certain depth. So null move pruning, there's a boxing analogy. So you give your opponent a free shot, and if they still can't knock you down, then if you went to the trouble of actually hitting them, you probably would have won. So that's the idea. So the implementation here is before doing a search, a full search on a position, you do a reduced depth search with the opponent to move. And if the score is greater than or equal to beta, you don't need to search that subtree. Right? So it saves time because the search is a reduced depth search. You usually use something like r equals 3 for the amount to reduce. So if your original search was the depth 24, this reduced search is to depth 21. However, there are weaknesses here. There's actually a name for types of positions where any move that you do is bad. So when you use the null move pruning heuristic, you think you're better off than you actually are. These are called zugzwang positions. And so in these conditions, null move pruning fails. You'll get a very bad result because it will just cut off entire branches of the search tree that it should have searched. I think in Stockfish there is an option to turn off null move pruning, or you can go into the code and disable null move pruning and then recompile it if you're analyzing one of these particular positions. And you can look up a bunch of them on Wikipedia. They're very interesting.
Unless somebody has changed it recently, Stockfish also is a verification search.
Okay.
After if the null move succeeds, then it makes a reduced search with the correct selection also.
So yeah, as Tord just mentioned, I'm just repeating this for the audio, Stockfish also does verification searches, even if it does cut off that particular branch to a reduced depth. So that's null move pruning. It's a fantastic heuristic. There's also late move reductions. So the idea here is that you have your move list that you're evaluating at a particular node. Since the move list is ostensibly already ordered by best to worst, then the late moves in that move list are usually pretty bad. They involve sacrificing pieces with no way to get them back, or moving your king out into the open, or whatnot. So you can just not search those as deep. So you search the first few moves at every node with full depth, and you search the remaining nodes at reduced depth. I think in the pseudocode that Tord put up on his own website, it was, I think, the first 4 moves or so. I think it changes depending on the stage of the game. But in his pseudocode, it was the top 4 moves from the move list at full depth, and then the rest in reduced depth. And I believe this cuts the effective branching factor down to 2. So where you originally had 35 as your branching factor, now you have 2, which is a lot better. So late move reductions, I think Tord is going to talk a lot about this in his talk. So if you want to learn more about late move reductions, attend his. So futility pruning is at frontier nodes, which are the nodes right before leaf nodes. You call the static evaluation, and you add a futility margin, like say 3 points. And if it doesn't raise the best value, you don't need to search that last move. So that's another time saver you can do as a heuristic for search. So that is futility pruning. Now let's talk about board representation. Woo! Yeah, OK. So how might you represent a chessboard? Well, you could do something like this, right? You could say, yes, I will just use characters. Blank characters, no pieces. Capital letters, white. Lowercase letters for black, and just use the letters. No, not really. So notice that there are 64 squares on a chessboard, and also a long data type is 64 bits. And most processors these days are 64-bit processors, so they can process these 64-bit words in one instruction. So you can essentially represent for all pieces, at minimum, for all pieces, for all colors, just have zeros for the piece is not there, and 1 for the piece is there, right? So maybe this is your most significant bit, this is your least significant bit. And so for white's king, you have a bunch of zeros, a 1 right there, and some more zeros. So that's 0x8, right, in hex. For black's king, well, then it'd be 0x8 and a bunch of trailing zeros. And for white's knights, as an example, you can do it. And then here's the answer. It's 0x42, right? Because you have 1 there, a 1 there. And so that's like the minimum representation of a chessboard using Bitboards. Stockfish stores a lot more than just, I think it's 12 that you need. There are auxiliary Bitboards for what pieces are attacking what valid moves there are for a piece, and so on, which makes move generation and static evaluation much faster. Let's see. Yeah, so those are Bitboards. And one thing you might often want to do with a particular string or long is figure out how many are set to 1. This is useful, say, in your simple evaluation function of number of pawns minus number of opponent's pawns. So you will want to do a population count. And so you might say, OK, we'll just loop over the 64 bits and count up the numbers that are set to 1. There is a faster way to do it, of course, which takes log time, approximately. So say you have your number A, this is 16 bits, and you want to count up how many there exist. You essentially reduce in a tree fashion. So you take every other bit in A, you right shift it, and then you take every other bit in A again, and you collapse them by adding it, and you keep doing it until you get to your answer, where you've basically moved all the relevant bits to the end, so you have 9. Alternatively, if you have any modern processor like Intel i7, i5, i3, and some AMD processors, and I think ARM is also adding this instruction, you can do a population count in one instruction. So they have POP-CNT is the instruction. So yeah, that's population count. Recap, I breezed through this very quickly. But so we talked about minimax, negamax, evaluation functions, alpha beta search, transposition tables, quiescent search, 3 search selectivity techniques, and representing boards with Bitboards. I can now, if there are any intermediate questions right now, I can take some. Yeah?
We heard Deep Blue beat the grandmaster of chess in 96?
Yes, 97.
97, doesn't care. And you have just told us a very decent amount of techniques to improve the calculation of moves.
Mm-hmm.
And I think it doesn't sound so high sophisticated. Why did Deep Blue only get the depth of 8 or 20 in some cases? What have they made wrong?
Should I answer it?
That's a good question.
Maybe I can help.
Here.
Okay, so depth is a bit fuzzy concept in computer systems, because the tree is not searched to some fixed depth. Some branches are pruned and reduced progressively, and others are extended with hard. And Deep Blue did a lot of extensions. So when it searched to that 8, really many branches were a lot deeper. And Stockfish is basically the opposite. So it is at depth 40, I was able about this later too also, but most of the tree is much shallower than that. Just a few branches are down to 40. So you can't really compare it directly. And regarding Deep Blue more generally, they had to make some sacrifices because they wanted to do everything in hardware, not in software. So they had hardware instructions for things like evaluating chess positions, generating moves and so on, specialized chess CPUs, you could say. And it makes sense that it's a bit more difficult to do the most sophisticated techniques that we have to do in hardware when it comes to complicated pieces of software. So it was very, very fast as measured in nodes per second, but the software was not the most sophisticated even at that age. And we have had many improvements since that time.
Any other questions?
So what kind of hardware would nowadays Stockfish have needed to beat Kasparov?
I think quad-core or 8-core processor would have done the job and like a decent amount of RAM. But these are like off-the-shelf components that you could just buy.
I think about the smartphone would be enough. They're fast. Fast smartphones laptops of 3-4 years ago, I guess.
Yeah.
But nobody really knows. We would need to have lots of games played under serious conditions between top computers and top humans. And we don't have that. So we can't really know. We're only guessing.
Yeah, I don't think there's really an incentive for grandmasters to play standard chess against computers because then they would just lose. So I think last year there was the Stockfish versus Nakamura matches, but these were modified chess games. So 4 games were played with odds. So Stockfish lost one of its pawns at the start of the game. And then I think a couple more games were played with Nakamura using Ridka for analysis.
That's a somewhat older chess engine.
Yeah, that's a slightly older chess engine. And Stockfish still won most of the games, right?
It won 3-1.
Yeah, 3-1.
2 draws and 2 wins to Stockfish.
Right. So that's with assistance and pawn odds. So you should check those games out. I think they're online if you're interested in that. Cool, okay. Oh yes, and so not covered, more search selectivity and parallel search. Tord will cover these in his talk. This one in particular is very exciting because this is incredibly complicated, or I think it is. Because generally alpha beta is hard to parallelize.
Now we'll explain why.
Yes, so go to his talk is basically what I'm saying.
But it's always depth first search. Can you avoid that?
Not really.
Well, why would you want to, first of all?
Well, if I don't know how expensive in time is looking at the rest of the branches, then I might want to come back. Well, you said that all the nodes are on the bottom, but
There's also part of the reason we do depth first is also that the tree is too big to store everything in memory. So the tree doesn't really exist as a data structure at all. We just
probably that is my question. So you don't store.
No, we have this transposition table that I mentioned, which is basically a giant hash table of previously encountered positions, but it's not big enough to fit the entire all the nodes you search. So you have to overwrite all the entries. The tree is simply too big to fit even if you have many megabytes.
So how beneficial is memory? I mean, do you use a lot of memory?
Yeah, this transposition table you can configure the size.
Yes.
It has to use as many gigabytes as you need. And usually it will perform a little better, but it's very slim because it can store more positions.
So yeah, for the transposition table, it uses as much memory as you give it. So on this system, I have 16 gigabytes of RAM, so I gave it 8 gigabytes to use. And it basically fills that up very quickly. And then uses replacement techniques like LRU or other things to figure out which ones it wants to overwrite. Yeah. cool. Oh, yes.
How long does it take to evaluate a given position?
Static evaluation is very fast. If you just run the static evaluation without doing any searching.
It's not exactly your question, but I think on a hardware like this Mac, Stockfish does something like 5 million nodes per second.
Yeah.
Position searched. And
Yeah.
If you have an iPhone, for instance, it's a bit more than 1 million per second. The most recent versions.
Yeah, so that's a good metric is nodes per second. And I think it's 5 or 6 million right now on this computer. Yeah.
How do you change the software? How do you judge if it's an improvement?
That's exactly what I'll cover next. I guess I'll start that part now. So this is called Fishtest. It's a framework that Gary Linscott created along with Marco Costalba. And it's exactly that, a way of verifying changes to the Stockfish engine that they are indeed better. So here's something about unit tests, right? It's very hard to unit test a chess engine. You can certainly test that the moves it generates are valid, or that it doesn't do terrible moves like moving its king into check or something. But you can't really test strategy because you don't really even know what the correct move is yourself. So we say goodbye to unit tests, and instead we have the Fishtest framework. So the idea here is you have your idea, you implement it in code, you send it to the Fishtest cloud, fun word, and then it runs it on a bunch. It runs computer versus computer matches, the new version versus the old version on a bunch of CPUs. These are not our own CPUs. They are donated by community members. So you can do this yourself too. You just download a little worker and it runs in the background. And when someone submits a change, then it will distribute a certain load of games to run on your computer. And so this is actually the map of where all these people are. They have the country of origin. So this is actually pretty nice. So it runs all these games, and then so it'll eventually decide after a couple thousand games whether to accept or reject your new commit, right? So did it cause an ELO gain or not? So in this case, we're like, yay. OK, so it uses, to determine how many games we run, we use a sequential probability ratio test. We keep playing matches until you're sure of, or of the null hypothesis or not. You calculate the log likelihood ratio as results come in. So results are streamed to the server. And you stop if it's less than alpha or more than beta, with alpha being the maximum number of type 1 errors that you want to tolerate, and beta being the one for type 2. And so some statistics. It was created in 2013 by Gary Linscott. Over 7,000 patches have been tested on this system with 178 million games played, 275 years of CPU time used, and Stockfish has gained 50 ELO by then. Some other information about this, which I didn't put on the slide. So there are, so these games are usually very fast. I think the time we give per game for a short matches are 10 seconds per game, something like that. And then for longer duration, we might give maybe like a couple minutes per game. But this is like, because you need volume of games, so we run these matches very quickly. But they're still meaningful. They still tell you whether a change is good or not. And so yeah, so you can access the queue at tests.stockfishtest.org. Yeah, question?
If these are games between engines, how do I introduce an element to make sure these games are all different? Do I start from random positions? Or
oh, yes. OK, so there's an opening book. So an opening book basically enforces some amount of variance in the beginning, because different moves will be chosen. Because you might say, well, let's choose in our opening book to do E4 with 30% probability, and D4 with another 40% probability, and so on. The other thing is, just due to the way timing system timing works, you never get the same game. Like if you run it even with the same opening position, the game, you will get different games. Like it will diverge very quickly. Especially at the time frame we run it at, which is like 10 seconds per game. Maybe Windows Update is running at the same time that your game is going, and it steals a few CPU cycles away. So now the game is different. Yeah, question?
But there's no explicit randomization within the engine, right?
I'm not sure about that. No, there is not. Thanks, Tor.
If you search with more than one thread,
yes.
Then that's inherently random.
Yeah.
So
yeah.
Get the same result in searching the same position twice.
Right. So
You get
thread
the same move,
thread
the same
scheduling.
search tree.
Yeah. So there is randomness introduced there, but not by Stockfish, by the operating system. Yeah.
So if you're running different versions of Stockfish against each other, is there any danger of optimizing for a particular opponent rather than optimizing overall?
Yeah, I guess. I mean, it seems to work out pretty well because, yeah, I guess that might be an issue. We do run regression tests, but against our own engine. So, I mean.
So are you optimizing for a particular meta game?
I guess so. Not really. Yeah, that's an interesting question.
In practice, it seems like self-testing, as we call it, testing with these older versions of result. It works pretty well, but it's misleading in one way. It tends to exaggerate the difference in strength.
Right.
So the difference in strength seems to be bigger than it actually is.
Right. You
so
can't.
in a way, that's an advantage because it makes it faster to verify.
Yeah. Yeah, so the ELO gain that you get out of testing a new version of Stockfish versus the old version is not entirely accurate. But it is a good metric to see whether you're improving or not.
Can you also train Stockfish for specific opponents?
For specific opponents.
Like real players do that, right? They know
Sure.
Fisher always play D4. Right?
I don't think we do that. I don't think we will. I think the philosophy here is that what we produce is the best possible move that you can do, right? So even an adversary that, I guess, okay, yeah, like Minimax is essentially if your opponent does subpar moves, then you have the advantage, right? Because you just do, Minimax optimizes for the worst case. So if the opponent does anything worse, then then it's better for you, right? So I don't think it's necessary even to do that, train specifically against a particular opponent. Let me just, since we're already here, this is the Q&A time. Yeah.
You showed in the beginning the numbers 9, 5, 3, 3, 1.
Yes.
And I just wanted to ask, there seemed to be man-made, and was there some effort in actually making them more accurate, or are they just the most accurate you can do?
The evaluation function?
The evaluation, yeah. Because as far as I understand it, you use them to evaluate a situation, and if you lose a rock, you lose, I think, +5.
Yeah. Oh, okay. So the evaluation function that I described there is not, or it's similar to in a sense, but not exactly what Stockfish uses. So the value for a rook in Stockfish is not 5, I believe. I believe it's less in the mid game, and it increases in value toward the end game.
I don't remember that use changed many times, but I don't think much more than that. Like 6,
Okay. And these parameters are tuned automatically. So I think Juna has a post about that.
Yeah, some, not all of them.
Okay.
Some
Yeah. But we don't just like pick 5 and say, we'll not change that, you know?
And how are they tuned?
How are they tuned? Does Torben want to speak to that?
There you go.
I must admit that I don't know these techniques Jona uses very well. So I will not go into any details there because I will just say something wrong. But anyway, you always have to play thousands of games. Even if something that to a human seems like an obvious improvement, adding some new knowledge that you just know is right about chess, and you implement it without bugs, and it's fast and everything, it can still make the program play worse. So writing a good evaluation function takes lots of time and frustration and patience. So so it's just trial and error and lots of testing.
Has anybody tried using machine learning to improve the evaluation function?
We haven't. There are people who have been experimenting with that, but as far as I know, not with much success so far. It could still be possible to be successful, of course, but apparently it's not easy.
So do you only use new games to evaluate that, or do you also study databases of human played matches?
No, we only play test games with a new version against an older one.
Because the Deep Blue people were quite proud that they used some grandmasters themselves to train it.
Using grandmasters is unfortunately not very realistic. They don't want to participate in testing. We could do things like trying to matching a grandmaster's move, for instance, to tune evaluation parameters to pick as many of the same moves as the grandmaster as possible. Which would be interesting if you wanted to emulate the style of some player. But it probably wouldn't be effective for high strength because computers are much stronger than humans anyway.
So most of the techniques you described are not really chess specific. So what happens if you let Stockfish have a go at Go, for example? Like where's the breakdown?
You want to or I?
I mean, the first issue with Go is that the branching factor and depth are much more than in chess, and I guess there's also the problem where I think that's the biggest problem is that
I think there is another problem that's just as big.
Okay.
The branching factor is a problem in a way, but it's also a problem for humans. So humans also can't search all lines very deep in Go because of the high branching factor. But the big problem is that it's very hard to write a good evaluation function for Go, I think. I don't know much about Go programming, and I'm not a good Go player. But in chess you have material, which is extremely important. If you have a significant material advantage, you basically almost always win. Even 2 pawns should be enough usually, and 1 piece is almost always enough. So you just use material as the basis for the evaluation function and add some simple stuff on top of that, and you already have a very strong player. But in Go, there is no equivalent to material. You have territory, but it's difficult to quantify, especially early in the game when the boundaries of the territories are quite fuzzy and not very well established. So humans are much better at recognizing patterns and have some intuitive feeling about vague territories, but it's hard to quantify it for a computer, I think. But as I said, I'm not an expert on computer Go.
yeah.
So does it still make sense for humans to play versus computers in chess, or is computer chess now an entirely different discipline from human chess?
Well, yeah. So at least in Stockfish, there is a skill level that you can set. So you can make Stockfish intentionally weaker and still play against it. And I think there is some research now into just like chess engines for the purpose of analyzing your own games so that you can improve, or training, I guess, so that a chess engine could potentially teach you about how to play chess. There is value in chess engines in for humans still. It's not like now we won't play chess ever again because computers can already do it.
So they're mostly used as analysis tools
Right.
by serious players.
Okay.
They use it for opening preparation, for instance, when they try to find new ideas in openings, they check it with the computer. And they also check their games after they have played them looking for mistakes.
Right. Yeah.
Grandmasters train against chess engines?
Yeah, definitely. Carlson, I think, publicly says he plays lots of games against chess engines.
Do you collect that data?
I don't believe that, but I'm not sure.
I think I may be wrong, maybe, but I think he's mentioned that. Double check me on that. Yeah.
So if you want to make your software weaker so that it's fun for humans to play against it, how are you doing it? So maybe just sacrificing the queen that doesn't make fun for a human. So how are you?
Right, okay. So Stockfish, basically, there is multiple principal variations, so you can turn that mode on, and you could always select, say, the third or fourth best move out of your list of moves. I think Stockfish, if you turn on skill level, if you reduce the skill level, it basically searches the top 4 moves and randomly picks one of the top 4 moves, is how it works right now. Something similar to that?
Something like that. But I wonder if it picks random between the moves which are within a given margin of the move.
Right, yeah. So, because like maybe the top 3 moves are like decent and the 4th move is sacrificing your queen, so you don't want to do that. But it does something roughly like that. Yeah.
Continuing the previous question, because that Gabriel asked, if you have grandmasters training against your engine, you do have a lot of input which you can train your engine on against grandmasters.
Not really, I don't think so.
We don't get much feedback from
Yeah,
the
we don't.
It would be fun to.
So I was talking about machine learning.
Then I'm not quite sure I understood the question.
Yeah.
You have a lot of data to make your engine train on.
Yeah, you mean by collecting grandmaster games?
Yes.
But what I was trying to say earlier is that probably not good enough quality. Humans are simply not good at chess. But you could try something to study your own games, play games at very slow time control and at very high quality, and then try to match it at much shorter thinking times, for instance. Maybe it would be an approach worth considering.
Yeah.
I guess, there was this point where Blue was winning against Kasparov, which was kind of remarkable because it was the first time that a computer won against a human or a good human player. But I guess there is a kind of different point where you can reach a point where a human, in addition to the Stockfish engine, say, cannot make any kind of positive influence anymore on the game. So giving a human player Stockfish and playing against the same version of Stockfish results in no added advantage.
If you mean if a human plus Stockfish can play,
yes.
Right.
And only Stockfish.
Yeah. So is that something that you are trying to
I think that
approach as a goal, or is that something that has already been reached?
I don't know if it's already been reached.
I'm also not sure. So
Yeah.
intuitively, I would expect that if you take Magnus Carlsen assisted by Stockfish, it's probably stronger than Stockfish alone.
Right.
But I don't know.
Do they have tournaments for humans plus Stockfish competing against other humans plus Stockfish?
It would be interesting. The problem is that human grandmasters usually demand a lot of money also. And, there's no longer much money in computer chess, unfortunately. So in the 1980s, 1990s, you could get really rich by programming chess computers. Not anymore.
Right. Any other questions? Yes.
So then, you said there's not much incentive anymore for human grandmasters to play against Stockfish. So on the other side, what's your biggest incentive? And you said there's not much money in it anymore. Are you maximizing for the highest Elo score or for winning a computer championship?
I think for Tord it's just a hobby, right?
It's a hobby.
Yeah.
So
Finding new search techniques?
Yeah.
Yeah. I don't think anyone is in it like for the money or anything. Yeah.
Can any of these techniques be reused in other fields of like artificial intelligence? So how much of this gets reused?
So search and learning, if you attended Dr. Lior's talk, are like different things. So like you couldn't apply alpha beta search to recognizing images or detecting speech. So
You could.
you could. Okay, never mind. I'm wrong.
There's definitely a point for synergy. For example, you were discussing grandmasters, how to use the data. So you can use the grandmaster data to learn the static evaluation function, or at least to get new ideas for the static evaluation function,
right?
Which is currently manually tuned. So it's only a small part of the system, but maybe you can be assisted by machine learning. So.
Oh no, like the other way around though. I don't like search for.
Yeah, I know. I'm just saying there are multiple points for synergy.
Right.
And for search, many times you want to evaluate your network quickly, or maybe you want to find out the exact active paths and so on. So.
Right. Yeah.
Okay, so is there one last question? No, then.